So, so this is the topic, the chapter that we were dealing with. So regression and correlation, and they mentioned that under this particular topic, we will be looking at interpret scatter diagram for bivariate data, and to calculate the equation of least square regression lines and use them to estimate values, and to calculate and interpret the value of the product moment correlation coefficient, and last but not least, to calculate and interpret the value of the Spearman ranks correlation coefficient. Now, like I mentioned to you before, if you are investigating the relationship between two variables, and in this case they mentioned x and y, and there was some example given there which you should have read, the weight at the end of spring x and the length of the spring y. So if you notice, they're referring to the same spring, the weight at the end of the spring and the length of that spring. So probably they are attaching weight to the spring, and this, depending about the amount of weight they are attaching, then you can clearly see what will be the length of the string. So they are being based on the same quantities right there. So that's what I'm talking. So they have been based on the same quantities right there. So we have other the number of hours spent studying for an examination X, and the mark achieved Y. So these two have a correlation together because the person spent time studying, so to see how well he or she will perform on the exam. Then here the students mark in a French test X and the mark in a German test Y. Nothing is wrong with this correlation as well because it's the same student which performed the two different tests, the French test and the German test. So you could have a correlation between the two tests, and to interpret in which test he did much better. So there you can have a correlation within his two marks from his French test and from the German test. Here, the diameter of a stem of a plant X and the average length of leaf of the plant Y. So once again, they are talking about the same plant. If you notice, they are not talking about two different plants, the same plant. However, they are talking about the stem, the diameter of the stem, and the average length of leaf of the plant, referring to the same plant. You cannot be, I think that you should have read some area whereby they talk about the rubbers and the shop, whereby and the health shop, whereby we're gonna look at it, whereby the rubbers have nothing to do with the shop at all. The rubbers are different, the shops are different, they have nothing to do with that. So that is not a good correlation that you have there. Now here, these are the different diagrams, and on the other page, they tend to explain it much better. So whenever we are connecting two variables, they are known as bivariate data, and we can plot this whenever we have the bivariate data, depending on the experiment or the investigation you are carrying out, then you will get what is known as a scatter diagram. So sometimes we call it a scatter plot. This is a scatter diagram, and if you can notice here that Hello, I come in different class. Yeah, different class. I don't start. Okay, then cool. Yeah. Okay, cool. So we are talking about bivariate data, and in this case, we have what is known as the dependent and the independent variable. As the word itself stipulates, the dependent variable tends to depend on the independent variable because the independent variable does not depend on the dependent variable. And there are certain quantities, especially when it comes to time. Time is usually an independent variable because right now you could be doing anything and time is still going. So usually we have the independent variable going on the x-axis and we have the dependent variable going on the y-axis. Now if you notice the first graph here, the first scatter diagram, if you notice after they have plotted the point, it's tend to condense what we are seeing, tend to move towards making a particular line. And if you notice how this line, these points are going, because as x tends to increase, y tend to increase. And if x is increasing while y is increasing, then that is known as a positive correlation. Now, if you would have noticed the one on the left hand side here, where it said y tend to increase as x increases, if you notice these points are more condensed towards making a line. So this relationship would have a stronger positive relation than this one. This one has a positive relation, but like I said, it depends on the clustering. Let me use the proper word, the clustering of the points that you have plotted. So this one would have been a positive correlation. If you notice this one here, as the value of x increases, the value of y tend to decrease, or y tend to decrease as x increases, and this is known as a negative correlation. And in this case, if you notice, the points are said to be haphazard. They seem not to decrease or to increase. So there's no correlation for that particular type of graph. Now, also, you should know that the independent variable is also known as the explanatory variable, and that the dependent variable is also known as the response variable. So you should be able to note those two. And here in this case, it said for example, if you place weight of 10 grams, 20 grams, 25 grams, 30 grams, 35 grams, 50 grams, etc., on the end of the spring and record the length of the spring for each weight, the weight is controlled, so it is the independent variable, and the length of the spring is the dependent variable because in that case, the length is depending on the mass that is being attached to it. So once again, this is a good correlation or a good investigation to be carried out. Then here we have the regression function. All that you're seeing here is that usually we tend to look for a mathematical relationship which will determine a regression function is basically a straight line graph that we are looking for. So it said here, having drawn a scatter diagram, you can then look for a mathematical relationship between the variable y equal f of x, where the function f, known as the regression function, is to be determined. And remember here, like what Shanti mentioned a while ago, that we are dealing with lines here, especially if you have a positive or negative correlation, you'll be getting a straight line graph. Even though one will have a positive gradient, that's the reason we call it a positive correlation, and the other one will have a negative gradient, it has a negative correlation because it tends to slope to the right. The other ones tend to slope to the left, and the other ones tend to slope to the right. So the one that slopes to the left will have a positive correlation. The one that slopes to the left will have, I'm sorry, the one that slopes to the left will have a positive correlation. The one that slopes to the right will have a negative correlation. Now it said here linear correlation and regression line. You must have a linear correlation before finding a regression line. Because if there is not a linear correlation, and linear correlation means whether it's a positive correlation or a negative correlation. But if you do not, then having a linear correlation, it links with the regression line because from the linear correlation, you are able to determine the regression line that you have from that particular correlation. It said here to consider the simplest type of regression function, y equal f of x. A straight line, if the point on the scatter diagram appear to lay near a straight line, is called a regression line, like I've mentioned to you already. You would see that there's a linear correlation between x and y. Here are some examples. We have looked at those examples. Here we have a regression line for a positive correlation, and for a negative correlation, we have a regression line as well. Then this is the piece that I mentioned that you should have known. It said common sense and care are needed when interpreting scatter diagrams. It said mathematically they may appear to be a relationship, but does not imply that there is a relationship in reality. You might find, for example, that over a period of time in a particular city, there has been an increase in the number of robberies and an increase in the number of health food shops. Now, if you notice, the robberies has nothing to do with the number of health food shops. They are two different entities. So it's saying here it would, however, be foolish to imply that there is a relationship between these two variables. What did I mention when I was looking at this by the relationship between the variables, the example on this side here? What do you notice about each of those examples? On the same page here, the page before me, what do you notice about these examples here? With regard to the example being given there. I'm talking about these. These are the examples here, the weight at the end of a spring X and the length of the spring Y, and the other one that I read. What did you notice there? What did I commented when it comes to those relationships? Anybody? What is it? Anybody seeing me? Hello?
Yes, sir.
Yes, sir.
Okay, so what would have been a difference here? Looking at the increase in the number of robberies and an increase of the number of health bishops, and looking at the other quantities that I've just shown you, the other examples. the other
That in the first,
relationships.
sir, that in the first example, the variables x and y work hand in hand, but in the second example, they are not working as it, sir.
Very good. Excellent. So if you notice on the previous example that I gave you that we are dealing with the same quantity, with the same object, okay? But in this case, we are dealing with two different populations as such. It's not the same individual or the same item or the same stuff that you're looking at. So indeed, that's what I was looking for. Now it said here, the appearance of a mathematical relationship does not imply that there is a causal relationship. An increase in one variable does not necessarily cause an increase or decrease in the other variable. So it said here, if it's appear from the scatter diagram that a linear relationship is a sensible interpretation, you may then attempt to find a model for the relationship in the form of a regression line. Now, the regression line is also known as, we call it, the best fit line or the line of best fit. And a line of best fit will be passing through, we would say, the median of between the points. So the number of points above the line should be the same number of points below the line at most of the time. However, there's a calculation using the mean square method that we're going to be looking at. How is it that we tend to draw a regression line? Because if we were to use a reference point, which is the average of the x values or the mean of the x values and the mean of the y values, you will get a point. That point will be a guiding point. But then how would you know the inclination whether it's going to shift right or left? And that is what we need to determine our to what y intercept it will be tending to. But just looking at some of it, you could know whether it's just a positive or negative relationship. So it says here that in the previous work, you may have drawn a line of best fit. I don't know if you have done that in science when you're at the high school, whereby you do investigation and they ask you to draw the line of best fit, whereby you take a median point and then you see the same amount of point below the other one. But that's not the correct way of doing it. That will just be a line of best fit in that case. So it said here that okay, attempting to draw it so that there are as many points above the line as below it, or as many points to the left of the line and as the right of it. So it doesn't have to be above or below, but it could be left or right of the line. The line should also go to a point. So this is one of them, which is the mean set of the two set of data. So usually when you are doing a scatter plot, you're gonna be having your bivariate data, whereby you're gonna having the x and the y values on a table. So what you will be doing, you're gonna be summing all the x values and divided by the total number of x values to find the mean. And also you will be doing the same for the y values, finding the mean of the y values, and then then whatever point you got there, that will serve as a reference or a guide to how you will be drawing your regression line, rather the line of best fit. Okay, so if you look here, So we have the line of best fit is the method that we use drawing with our eyes. Okay, it said there this method known as drawing by the eye is rather haphazard. There is a mathematical way of fitting the regression line known as the method of least square. So we will be looking at the method of least square, and this is illustrated in the following example. But not much has been done with this here because they didn't show the full working of this to get the regression line here. But I will need to show how is it that we get that there. So we have our time x in minutes, and we have our mass in grams, y in grams. So we have 5, 7, 12, 16, 12, 20, and the corresponding mass for these times. These are the results, and they can be illustrated on a scatter diagram. All you need to do, you will notice that you will have nothing, you will only be dealing with the first quadrant at all times. When doing scatter diagrams, you won't be doing with the other three quadrants. Excuse me, the only quadrant that you will be dealing with will be the first quadrant. Then you need to have a linear scale on both sides and a suitable scale for both the y and x axis depending on what relationship you have. Then you're gonna be plotting 5 to 4, so they go 5 here to 4, that's the first point. Then 7 to 12, so this point here is 7 to 12. Then 12 to 18, so this point here will be 12 to 18, the x. And then we have 16 to 21, which is this other point. 16 to 21, and then 20 to 24, which is this point. Now, if you notice, from what you can clearly see that this graph will have a positive correlation because as the value of x are increasing, so are the value of y are increasing. Because y is increasing as x tends to increase. Everybody got that? Everybody got that part?
Yes, sir.
Now, in order for them to find this mean, x bar, y bar, this is x bar, a bar is on top, calling the mean of x and the mean of y. Now, in order for us to find the mean of x and mean of y, then we're going to go and take the x values first, add them, 5 and 7 will be 12, 12 and 12, 24. Adding all of these, you're going to get 60, divided by the number of x values, 5. So 60 divided by 5 is what gives you this 12 that is here. So that will be the mean of the x values. Excuse me. And to find the mean of the y values, you do the same. You need to add up 4, 12. So this will be 34. And adding all of this together, what do you get? 59. So you're gonna, whatever you get there, you divide it by 5 as well. So what value you get there?
Sir,
Yes.
I got some people now in the waiting room. I should be unsure.
Mm, okay. So like I've said before, this is how we obtain this point here. If you would have added all of these, what do you get? Because this would be 45 plus 30, that's 75, 79. So divide 79 by 5, what do you get? Somebody should have your calculator there, man. I'm asking a question.
15.8, sir.
Okay, you get the 15.8. I want to show how we obtain the 12 and the 15.8 here. It's the mean of the x values that we obtain the 12 by adding the x values. And to obtain the mean for the y values, we add the y values that are here. Any question based there? So that will be our guiding point. So this is the point that they plotted here, which is the x bar, y bar point, which would have been the 12, 15.8. However, if you notice, this is showing you, that's the reason I'm telling you that having the mean points, this point here, that doesn't determine the correct, it's just a guide for you to draw your regression line. If you notice, two different regression lines are being drawn here using the same mean point, which is here and here on the line. Now, it said there below that in each of the attempts, the dotted line goes through x bar, y bar, and there are 3 points above the line and 2 points below it. Yet neither of these lines is correct. You see what it's telling you? Yet neither of these lines are correct. Now diagram 3, which is this diagram, shows the true line of best fit. It has equation y equals 1.15, which should have been the y-intercept, and the gradient should have been 1.22x. This equation has been calculated using the method of least squares, which I'll be showing you how that is being done. Okay, so using the method of least square, the calculation are shown on page 123, which we're gonna be looking at shortly. And then if you notice here, this is the correct line. It said there, note that the time x are chosen by the person holding the stopwatch. So x is the independent variable. The value of the mass y depends on the result of the chemical process. At this time, therefore, y is dependent variable. If you were to repeat the experiment with the same value of x, you would most certainly get a different set of values of y. So what this is telling you, that whenever you create any experiment, you could be carrying out the same experiment as before, yet you will still not get the correct, I mean, the same values that you have obtained for the previous one. So each experiment counts on its own. So here it said they were talking about the masses and the chemical and the time for the chemical processes to have occurred. Then it said here that if you were to repeat the experiment with the same values of x, you will almost certainly get a different set of value of y. So for a fixed value of x, you could have several different values of y, all in the same vertical line on the scatter diagram. That's the reason in science, when you're running an experiment, they ask you to do about 3, 4, 12. The value of x remain the same, and then you're gonna be running that experiment for those same values for 4 different trials, and then you take the average of those, in order for you to get what we said, not accurate, but not exact, but a much more better, well, accuracy, so that you can get a better accuracy of the information that you have gathered. Now we have the least square regression line of y on x, because we also have the least square regression line x on y, which we're gonna be seeing as well. Now, here we are talking about the same, said here to find equation of the least square regression line of y on x for the chemical processes. But all this is telling you here is that there are several things that you need to do. In this case, what they did was to take the summation. Remember the sign that I gave you when we were looking at raw data and group data? We said that in order for us to find the mean of raw data, which is x bar is equals to the summation of x over n, where n is the number of observation and the summation of x is the total, is the summation of all the observation that you have. So basically, this is what this is talking about here. So it said here a line that fits the data is one that makes the summation of m square one as small as possible. It is drawn so that the summation of m square sub 1 is minimized. This line is called the least square regression line 1x. Now, these are the same points that we have here in terms of m. And what this is showing you, that even though you're going to be having your reference point here, in each case, because this is showing you the different representation of join this graph, and this is showing you a vertical line, the distance of a vertical line away from this M1. If you notice from this one is going down, this one here is going up, and this one here is going up. But the vertical distance away from the line tend to differ. Now, which one of them you would tend to choose? Well, you're gonna tend to choose the one that have the least squares, which would have been diagram 3. If they would have asked you to interpret, if they would have gave you like a couple diagram and asked you to, what would have been the line that shows the best regression line, or which would have been much more accurate. So you need to look at the vertical distance away, and the one that has the least from the point below will be the one that you will take. Now it says here useful formula when calculating regression line. Like I mentioned to you before, when we are calculating the equation, we need to look for the mean of the x and y values. So first of all, we look at the x data. And what you need to find about the x data, you need to find the mean of the x data that is given to you. And then remember, I gave you a formula for variance as well. When we were looking at our data, that our standard deviation, we said that the standard deviation is the square root of the summation of x over n minus the mean square, x bar square. And that the variance, which we use s square, is equals to what under the root sign for standard deviation, which would have been the summation of x over n minus x bar r squared. We have looked at all of that. Now it said that the variance is usually written as a square, but to distinguish that, it is the variance of the x data. So you would write x squared sub x. Sub x meaning then that is the variance you're finding. So if I ask you to find s sub x, you are finding the variance for the values of x. Usually, however, when working in the context of regression and correlation, the variance of x data is written as Sxx. So these are things that you should have remember, but like I said, we didn't look at these formula, this one over this side, where we use the assume mean. We didn't use the assume method. So this is the one here that you're gonna be using to find the variance. Because the extra x is showing you that you're finding the variance of x. Because remember the 1x is showing you that you're finding the, well, we're gonna look at the symbols when we look at that. But what I want you to notice here, this is the formula that you're gonna be using for the variance. So that will be summation of x squared over n minus x bar squared, which is the mean. This one is the same as this here. These are two different formula, but the same thing. So you could either use this one or that one. Then for the y data, to find y bar, which is the mean of y, the summation of y over n, I've shown you that. And to find the variance of that SYY, this is what we have, summation of y squared over n minus y bar squared. Then to find the covariance is the combination of the x and y data. So that's the reason they call it the covariance. You're gonna be multiplying them together. There's a formula for you to do that, which is this one, the summation of xy. So you're gonna be multiplying x and y, then you add them up and put it over the total numbers that you have. And then this is minus the mean of x, the product of the mean of x and the mean of y. Now there's another way of representing it. In some book, rather than the small s, you're gonna be they use a big S. So that's just a difference. And here they tend to spread it the same thing, summation of n. This is telling you the mean of x over the mean. Can we could split this as summation of x over n? So it's best that we just stick to the basic ones, which give you the same thing rather than move into complications. So the equation of the regression line y on x. It says here you are probably familiar with the equation of a straight line in the form y equal mx plus c, which all of you should know. This is the equation of a straight line, and this is known as the slope-intercept form, whereby in this case, m is the gradient and c is the y-intercept where the line cuts the y-axis. So each straight line will need to have a gradient, and also it needs to have a y-intercept where the straight line cuts the y-axis. Now, in the case of a regression line, we tend to use A and B. So in this case, we tend to use B for M, which is the slope B, and A for the intercept. And if you notice how the equation is being formed here, for regression line is different from that of a straight line graph. They tend to be shifted around, whereby the intercept comes first here, followed by the gradient B here, the gradient M coming first, followed by the y-intercept C. But it's the same thing. It's just a matter of differentiating a regression line, which is still a straight line from that of an actual straight line when it comes to straight line geometry. So the one below here showing a regression line, and the other one above here is showing a straight line. So the equation here is y equal mx plus c. Here it's y equal a plus bx. Are there any questions there? Are there any questions? I'm not hearing you.
Not really, sir.
Okay, then here to define the regression line, you need to find the value of a and b. Just like when we look at straight line geometry, you need to find m and c in order for you to find the equation of the line. Then the gradient b, you need to find that. And you see, once again, they show the two formulas here. B is equal to the covariance of x and y over the covariance of x. I mean, over the variance of x. The covariance of x and y, and this is over the variance of x. He said node B is known as the regression coefficient of y. So when they ask you to find the regression coefficient, they're asking you to find B. Remember, we have formula for SXY, which is we look over this side, and we also have the formula for the variance of S, which is this one here. And we just calculate it. Usually, what you need to do, you will always be provided with the values of X and Y. So you need to do a table like this all the time before you can calculate the regression line, the equation of the regression line. So x and y will be given to you. Then you need to find x squared, whereby you square all the x values. Y squared, you square all the, and then the xy, you have xy. Now, the summation of x, that is 60 when you add up these. The summation of y when you add these up is 79. The summation of x squared is 874 and y squared. So you're gonna be having this table. Then from that you're able to calculate the mean for x, which is the summation of x, which was 60 over 5, and the mean of y, which would have been 79 over 5, which is 15.8. The same thing that we got on the page when I told you that this is 12 and the other one was 15.8. Then they go and find the covariance of xy, which is 37.6. And once if you notice, they substitute here the xy, which is 1136. Once again, how we get the xy, it's 5 times 4, 20, 7 times 12, 84, 12 times 18 give us 216, and so forth. So here the summation of xy, n is the number of values that you have. So it was 5 of the values, 1, 2, 3, 4, 5. So over 5, so 1136 over 5 minus 12, that's x bar, and then y bar, 15.8. But you could use bucket for this rather than times, so that doesn't look. So what you will see when we do an example, it will be much more simpler than this one. Then they continue. Then they find B. How they calculated B? They take the SXY, which was the 37.6, divided by the variance of S, which is 30.8. And when they simplify that, they obtain 1.2207. And to 2dp, it is 1.22. So what we do next there, we substitute that into the equation that we have to find the other value A into the equation so that we find A, just like y equal mx plus c. In this case, we are using y equal a plus bx. So you would have had b already, and then you can use the point, and the point you're gonna be using is the mean points, the one for x and the one for y. So if you notice, a is equal to y bar minus bx bar, and then that is what we obtain. A is equal to y bar minus bx bar. We know that that will be 15.8 minus 1.2207 times 12, and then they give you, by calculation, you obtain 1.1, negative 1.1, I mean 1.15. So the equation of the regression line, since you have found A and B, then remember the value of A is 1.15, which goes here, and then B goes here. And that will give you the straight line graph that best represent the set of data. Are there any questions thus far?
Sir, so by plotting the graph, we're going to use x and y, right?
To plot the graph, yes, we use X and Y.
And then the what we're going to use for us to guide ourselves will be the 1.15 and the 1.22, right?
The 1 point,
The
the line,
1.15 and the 1.22, right? That's what we're going to
yes.
use
Oh,
to
yeah,
to
this is
to
the
do the
line.
line.
Yes,
Okay.
you're just gonna be substituting the values of X in here. Then you get the value of Y. You're gonna get a straight line that represent that will represent the scatter point points that you would have had on your scatter diagram.
Okay, sir. Thank you.
Okay, you're welcome. Are there any other questions? Are there any questions?
No, sir.
Okay, okay, no problem. And this is another way they could use using the biggest formula. But like I said, we won't be using the biggest formula. We're gonna stay with the smallest so that we do not have any sort of confusion. Are we clear with that?
Yes, sir.
Okay, we're gonna end there for today. If there are no more questions to be asked. And have a nice weekend, all of you. For those that are present, the others, you see how many are absent already? I have to penalize those students that will be removing some points because they should have been here. They have no excuse. Okay, have a nice weekend. Those that,
Thank you, sir. Same.
Same to
okay,
you,
you're
sir.
welcome. Okay,
Same, sir.
okay.